Welcome, everybody. I'd like to start today by having you press the raise hand. If you can hear me, this is Mark Anderson speaking to you from Minneapolis, Minnesota. On your control panel, you'll see an icon that looks like a hand. Alan, I see right away. John, I'm just kind of reading through. We've got over 200 attendees at this point. Wendy, at the other end of the alphabet. And in between, lots of others. Great. Okay, so that gives me a good sampling. I expect that the population of people listening is represented by this sample and therefore can hear me. If there's any issues, please get back to Staddies directly and they will give you directions to the recording of this talk, etc. So let me begin. Again, I'm Mark Anderson. I am a principal with Staddies here in Minneapolis. My background is professional engineering, chemical, and I'm also a certified quality engineer. I've been using design of experiments, DOE, for some decades now, and I'd like to share with you how you can know the score for multi-factor strategy of experimentation, screening, characterization, optimization, and ruggedness testing. That spells out SCOR, S-C-O-R. So let me begin the show. So again, I'm trying to convey to you a good strategy that's multi-factor for design of experiments, and it involves screening, characterization, optimization, and ruggedness testing, hence the idea of the score that we need to know. Now, again, I want to welcome everybody. People are still coming on. We're up to 234 at this point. So because of so many people being on board, I'm going to keep you on mute throughout the presentation. And then as far as chat is concerned, it's going to be hard for me to keep up with that. However, if you do put in some notes, I'll stay on afterwards and I might be able to provide some answers. However, it's going to be much better if you would just jot down any questions that come up during the presentation, note the slide number, and then send an email to me, mark@staddies.com. And then, as I mentioned, if there are any difficulties or if you want to share this with your colleagues, the presentation slides will be posted and may already be at this website. Go to our main site and you'll follow through to where the webinars are. And you'll also see a recorded session, hopefully if everything goes well. So once again, press that raise hand button if you're with me. Okay, and I've got, going through the middle part of the alphabet, I've got Patrick and I've got Heidi, if I'm pronouncing that right, probably not, Nicholas with one H and Nicholas without an H, et cetera, et cetera. So thank you for that. I'm going to put the hands back down again. And watch out, from time to time, I may ask you to please give me some feedback by pressing that raise hand button. Without any further ado, let's press ahead. And what I want to do first is just manage expectations by providing you the WIIFM, or what's in it for me. WIIFM. And we always want to think about coming into a presentation, what is it we're expecting to get out of it? And presenting, I'm trying to figure out what the audience hopes to take home with them afterwards. And ideally, I've always felt that if you can come out with, one or two really great ideas from, say an hour's worth of attendance, that's a great, ROI, return on investment. So in this case, what I'm really trying to do is, by example, lay out a really good strategy for experimentation. And the ideal would be that using multi-factor testing approaches, you get a maximum efficiency and also effectiveness for the development of a robust process. And by following this strategy, you can map out a sure path that will converge eventually on a sweet spot where you get the most desirable combination of process and product. So really, I think whether you're new or experienced at doing design of experiments, this talk will be for you and it will help your organization's bottom line or whatever your mission is, for example, if it's an academic. Before the score, there has to be some kind of great thought, a great invention. And I just have to pass along from 3M Company, which is just down the road from where I live in Stillwater, Minnesota, their world headquarters. My son-in-law is a PhD organic chemist that works in their tech service. And of course, they're known, amongst other things, of inventing the Post-it note. And Art Fry was the one who came up with this serendipitous idea to make a semi-sticky note. I love the Post-its, so I highly recommend them. Another invention that came from Minnesota is this Nerf. So that's another Minnesota inventor, and his name is Rain Geyer. If you want to work off some stress, pick up one of these little Nerf balls and start throwing it around. It shouldn't cause too much harm. And then last but not least is Spam, which was, of course, invented by Hormel in Austin, Minnesota, which is my hometown. I was born there. My dad was a civil engineer. He's a master's degree, and he worked at the plant in Austin. So Spam is really a good comfort food for anybody living here in Minnesota. Great to have when you go camping. My point, though, here is that before we can start refining a process or improving a product, it's got to be invented to begin with. So let's not overlook that and give credit for the first principles and the geniuses behind the beginning point. So invention is the start. Okay. But now that we have an invention, we're going to have to start coming up with a way to produce it, manufacture it most efficiently, and hopefully get all the product attributes that we're aiming for accomplished. So my main focus in this talk actually is on process. There's a whole nother approach that is similar for mixture and formulation, but it's very similar to this. But our focus today will be on process. So we're going to begin with screening. And something that may not be intuitive is that at the beginning, if you first think about possible unknown factors off to the side here, maybe do some kind of a brainstorm with a fishbone diagram, get your group together and think about, what might be the factors that affect this in terms of materials, the methods, the people, and the machinery, and also the environment. It's kind of brainstorm. You're likely to come up with lots of things that nobody's ever tested before. And so a good way to do this is to hold off known things, things like time, temperature, concentration in a chemical process, kind of hold those off, and then focus on maybe some unknown factors, like what happens if we change the agitation rate? Does that affect things? And you could come up with lots of ideas with a brainstorm. And I would suggest that you start off here with the screening with maybe 8 factors, represent that by the letter K, and do this in 16 runs, represented by the big letter N. And this would be a very good screening design, is what we call a resolution 4 design. And in Design Expert, you'll see these yellow coded. They're sort of in between on the stoplight configuration of green, which is a go-ahead design for looking at interactions, and red, which comes down here at the end. And these other designs, the green ones are resolution 5, and red is resolution 3. So each one of these types of designs has a place. But at the beginning with screening, we're going to want to go with these medium resolution 4, because these will be very good for determining main effects. Okay, so what we're going to do is screen, let's say 8 factors and 16 runs. And hopefully out of that, maybe we get about 20% that are the vital few and 80% fall off. And now we can merge together known factors with ones that we've discovered in this screening and do a second part. And now we're getting to the C. So we've got the S for screening, the C for characterization. Now we're up to the C part. And now we're going to do this higher resolution 5, which is a green design, and we're going to look for 2-factor interactions. In addition to, checking out these main effects once more, now we've merged in these known factors. Now at this point, if we had 3 known factors off here, and maybe we get 2 of them coming in vital few and 6 are thrown off, apologize for all the scribbling here, but I like to think by writing as I speak. So hopefully this is somewhat helpful. So we now have a total at this stage of 5 factors, 3 that came in from before that were known, and 2 that came out of the screening. And if we do another 16 run design, this is actually a design that would be characterized as 2 to the 5 minus 1 because it's a half fraction. And the first one actually was 2 to the 8 minus 4, which is a 1/16th fraction. So using the design builder screen on Design Expert, we can accomplish a tremendous amount in terms of screening and characterization. I'm just going to pull that up, and you can see here on Design Expert how we have the white diagonal. And this is actually the full factorials. And then we have the green designs, and I'm now at this point here where I've done a half fraction. All right, now I've thrown a lot of scribbles on. I've alt-tabbed over to Design Expert. And what I'm going to do is just ask you to press that raise hand again if you see on your screen right now the Design Expert Design Builder. According to my information, this should be showing. All right, I see hands coming up. Okay, great. I'm going to put them back down again. And from time to time, I'm just going to ping you guys to make sure that you're with me, because over the years and giving these presentations time and time again, I've found that lots can go wrong between here in Minnesota and all the way around the world to where you're at. So now we've gotten through the S and the C. Then the next phase will be that during this characterization, we add center points. And these center points at the middle of the design space can provide us with a test for curvature. If there is a curvature in the system that's significant and appreciable, then we're going to move on to the optimization phase, and we're going to use response surface methods. The acronym for that is RSM. And this will actually give us a really good idea of a possible peak of performance. Okay, if we're looking for maximization or a minimization, we'd be looking for, a valley. So once we do that, hopefully we'll hit that sweet spot. Then all that's really left is to confirm the results. And for that, I really like this ruggedness test, which gives us the OR in SCOR. The ruggedness test is a very good way to see if the results will hold up out in the field by systematically in a multi-factor way, throwing as many factors as you can at the process. And for this ruggedness test, I really like the Plackett Burman designs. And these Plackett Burman designs are very handy because you can do, say, 11 factors in only 12 runs. Now you have to be a little bit careful in doing these saturated resolution 3 designs that you maintain power so that if there is an important difference, you'll be able to detect it. So what I'm going to do is I'm going to demonstrate SCOR. And I'm going to demo this by going through an example. The example I'm using is going to be welding. Now, this example I like because it sort of straddles between people that are making things and those that are producing stuff. And I'm a stuff guy, okay, being a chemical engineer, I'm more familiar with process industries. And that would be things like chemical, of course, food, pharmaceutical, paints, all kinds of stuff that I'm familiar with. On the other side of it, and probably less use of DOE is seen here, would be people making things like automobiles. Now, the welding, of course, kind of straddles this because it's really like a process, but you're making a thing. So this is an example that I kind of like, and I presented this to the Naval Surface Warfare Center, for example, for test and evaluation. And this is actually an example that comes out of the US Navy. But it's something that we can all kind of relate to. And we have a problem that the welds are falling short of what we need. So the engineering team has a brainstorm, and remember my suggestion of using the fishbone diagram. And they come up with 11 factors, 9 of which are unknown that need to be screened. And we have 2 that we're going to hold aside that we're pretty sure will affect the process. Now, other factors you're going to hold fixed, and things like humidity you might monitor. So there's actually other variables that are outside of this, but they're not going to come into the design of experiments. So here are 3 designs that they think about. One is, let's try to do only an 8-run standard fractional design, but saturated with 7 factors. And that would be here on our design builder. Now it's red. That should make you stop and think. This type of design, George Box said, is like kicking the TV to make it work. It's not a very good design to screen. And besides that, we're missing 2 factors. So this is rejected. So number 2 idea is screen all 9 factors in the classic 32-run standard fraction. Okay, let's see where we're at. 9 factors and 32 runs. Okay, that's yellow. That's better, but that's a lot of runs. Too many runs. So now, number 3 is, let's choose a modern minimum run screening design. And these are shown in the next line at Design Expert under minimum run screen. So here you can see we have 9 factors in only 20 runs. And we would have had to do with the regular 2-level 32 runs. So we've actually saved from 32 runs down to 20 runs, 12 runs. And you could actually do a minimum, a true minimum of 18, which is 2 times the number of factors. However, then you don't have these extra 2 runs just in case something happens. So our choice is going to be, and the engineering team chooses number 3. Now, how many of you feel like that's a good choice and that we put in the 2 extras just in case something might happen, something bad, like the machine running down, breaking down, or something like that? Raise your hand if you think that's sensible. If you're with me on number 3, and trying to go with fewer runs, but not so few that you're right down to the bare bone. Okay, hand raising, Adrian. Okay, I'm just kind of paging through here. And if I don't read your name out, Zach, or whatever, that doesn't mean I'm overlooking you. It's just we got a lot of people online, Wendy, etc. Okay, good. Putting the hands back down. You're with me. Great. Okay, so let's see what happens next. Okay, before we get to that, I just want to throw up this little, I call it a sell sheet, to indicate, the value of doing these minimum run designs that Staddy's invented in the early 2000s. And this was from our PhD advisor, Gary Ohlert, from University of Minnesota, and our founder and our top gun, Pat Whitcomb, came up with these ideas. And then my job is to try to write them up and explain stuff. So I explain how to screening process factors in the presence of interactions at this conference in Toronto. So I played a little role in it as well. But it's hard not to be sold on this, because like in this case with 9 factors, we can cut down from 32 to 18, and going to the +2 puts us at 20. Not the absolute minimum. And you can see how we can get by with many fewer runs. And this would be screening for the main effects. Now, when we go to the characterization, we have other designs that can detect 2-factor interactions. Of course, you're going to have to do more runs. This is a higher resolution 5 versus 4. But again, we can use these minimum run designs to save lots of runs. All right, so that's what we're going to do. Now, here are the factors. I won't belabor all the different factors that they're studying for this welding, but they're not real sure, what's going to happen. One of these factors here at the end actually is a categoric factor, and that is, should we prep the edge, yes or no? So let's take a look at the results from the study. To begin with, just tabulated down below here, we can already see that some are going over 50,000. So that's very promising. But now what factors that we're looking at here actually affected the response? We've got to look at our data using Design Expert. What I'm going to do is cancel out of this and open up this weld screen, and then I'm going to rebuild it to show you that I'm in this minimum run screen design for 9 factors. In 20 runs, I'm going with a +2. And here are our names of factors Units of measure, it's pretty easy to enter in. You can enter in categoric factors, no or yes, very straightforward. And the aliasing is good in the sense that all main effects are aliased only with 3-factor interactions, which generally you would assume are nil. And therefore, this will give you a design that'll give you clear estimates of the main effects. Never mind the 2-factor interactions, we're not going to worry about those too much right now. And then we can do a power calculation. They're interested in a difference of 1500 PSI, and their noise for doing welding based on repeatability studies is 900. And therefore, with this many runs, with 20 runs, we're able to get just enough power to be able to detect the differences we're interested in detecting. So we have a very handy power calculator. So everything's a go. We're ready for liftoff here. And so now we collect the data. Now over to the right here are the tensile strength results. And what I'm going to do is sort those just to check and see if we get any over 50,000. And we do. Okay, now I'm just going to go back over to my control panel, just being paranoid about how internet works and everything. Do you see those 3 really good runs at the bottom now that are over 50,000? Yes? Good, okay. Now you're getting condition raising the hand. Thanks, Thomas and all. All right. So the next thing I'm going to do is I'm going to look at graph columns. And I won't spend a lot of time on this, but there's a very handy facility to just simply look at each factor one at a time. This was suggested by Andy Kirsch, a statistician at 3M Company, as a way for users that are not super strong on statistics just to get a quick look on the different factors. And the ones that are strong colors, like this substrate thickness, is a strong red. That means there's a high correlation. As the thickness goes up, also does a tensile strength. So that gives us kind of a pre-analysis of what's going on. But the real results are telling from our half normal plot. And here we see the effects that are standing off to the right, which involve the angle A, the substrate thickness, the edge prepping turned out to be an important factor. We didn't know that. And then there's an interaction here, but that interaction could be a number of other interactions. So we have to be a little bit careful about that. But it probably is interaction of A and B because those are strong main effects. Then we can look at the aliasing to remember that AB actually could be a number of other things. Now going back to the effects screen, we can also look at a very handy plot that is great for presenting to managers or sponsors, which is a Pareto chart, and we can see how substrate thickness stands out and so forth and so on. And there's lots of little effects that don't matter. Those are going to go into the error pool, which are providing us with an estimate of error or residual, and we can test then the factors we've chosen against those, and we can see they're all highly significant. Then we get into the diagnostics, but the main thing is there's no abnormalities on this normal plot of residuals. So that's good. And then the model graphs, and we see that there's an outstanding result up here, for example, at the high angle with the high level of factor B, which is the substrate thickness. And we could do more with this, but remember, we're just trying to screen. Now, one of the interesting things is the edge prep. And this edge prep says, yes, we should do the edge prep. That's a little time-consuming step, but it's worth doing. And when I click this point here, these least significant difference bars, which show potentially a gap, can be clarified to indicate there really is a gap, that when we do the edge prep, yes, it gives us significantly better tensile strength at 95% confidence over not doing the edge prep. So this is a very handy tool for us to look at that edge prep. So basically what we have at this point, and I'm showing the Pareto plot now on slide 9, is that we've got 3 of the 9 factors that we screened by doing the minimum run resolution 4 design. And we found that 3 of them, which are the substrate thickness, the angle, and the edge prep, and never mind this interaction for now, survived. So those are the vital few, and we've thrown off 6. Remember though that we had 2 that we kept aside. So these are going to merge in, and now we're going to do a second series of experiments or runs that's going to characterize. However, the engineers looked at this edge prep, and they don't want to be messing with this back and forth all the time, and it's not part of an interaction. So they decided that it made sense to them, and they thought it probably would, that they should do the edge prep. So they just decided after this to fix the edge prep at the yes level. Okay, so that way they're just going to go ahead and take that gain right away and quit messing with the edge prep. Just leave it as it's something that has to be done. Now we're on slide 11, and at this point we're shifting to characterization. So we've done the screening, and now we're doing the characterization. We had 2 factors that bypass screening, and they were the current app range, and then we have another categoric factor, which is a type of stainless steel. Those bypass the screening. And then from the screening, we've got 2 of the 3 with the edge prep being held constant at the yes level. All right, so now we have 4 factors, and this makes a very convenient number of factors because we can simply do the full 16 run or 2 to the 4. We don't want to do only 8 runs because that would be a fractional that would be too low in resolution, that would alias the 2-factor interactions. So we're just going to do the full 2-level experiment. Now at this point, we're going to add 3 center points, keeping in mind that there's going to be 3 center points for the stainless steel 35 or SS35, and 3 more at SS41, and these will be at the middle of these ranges. So we'll have 70 for the center point on angle, 10 on the thickness, and do the math on the middle of 125 and 160. All right, so that would form a center point, and we'll do 3 of those at each type of stainless steel. So now we're moving ahead to the next design. However, as expected, all 4 factors did emerge as main effects, and or they were involved in 2-factor interactions, but the curvature came out significant. And it was appreciably curved. In other words, the difference at the middle was so much more that it's not even worth using this design. We need to move to the next level, which is the response surface methods. Okay, so that's what we're going to do next. So I'm not going to demo this design because it just right away tells us that, whoops, we've gone too far with 2-level designs, even with center points. So now we got to move on to the next level. But there is a gain from this, and that is we did see in this design that the SS41 was significantly higher across most of the range of angle. It's a pretty robust condition. And other than the SS35, when you got to the high angle, did begin to overlap with the SS41. The SS41 was the best, and the center points on the SS41 were definitely higher. So let's keep things simple and just eliminate SS35 from consideration and only carry SS41 forward from here on out. Does that make sense? Press the raise hand if you're with me on that. Tom, Tony, etc. Okay, great. Just check it and make sure that you're getting this. All right. Now we're ready to move on to the next phase, which is the optimization. So we've got the screening done. We've got the characterization done. And yes, we did see curvature and it was important. So now we're going to do the optimization by RSM. So we're up to the O in our score. All right. So what happens next? Well, for one thing, I just want to point out that we have to be a little bit careful not to start off right away with RSM, because that would create a huge number of runs And there's really no reason to, if you're starting off in an area like Minneapolis, Minnesota, and you're wanting to get to somewhere fun, you know, like the mountains, then you want to drive very quickly across the western Great Plains of Minnesota. And if you know your geography, we're going to probably cut across Iowa. And eventually we're going to get into Nebraska and western Colorado, eastern Colorado. And eventually we're going to get to somewhere fun like Boulder, Colorado, and Pikes Peak. And that's where we're going to take our time to do the RSM. But we're going to use other techniques, two-level design, screening characterization, first principles knowledge, and so forth. And then we're going to try to get into this region of interest and then apply the RSM. Now remember, this is all empirical. And George Box, who invented RSM in 1951 with Imperial Chemical, he was very sharp and he recognized that all models are wrong, but some are useful. So we're just trying to get an approximation. And we're going to apply RSM, and then we're going to get a way to predict the response Y as a function of X. And we're going to use something called a quadratic equation. That's kind of the go-to for the RSM. That'll give us a much better picture of the curvature in the center of this welding space, you know, so that we can see if it's a pure peak or a rising ridge or something like that. Using factorial design to get close to the peak with the S and the C, and then using RSM to do the O, the optimization to climb it. So here we are on our flow chart. We came out of the screening with 4 factors by fixing the edge prep as yes. We came out of the characterization recognizing that there was curvature, but then we fixed the steel at the SS41. And so now we have 3 factors, which is manageable for our response surface method. And even better yet is what George Box came up with was a very smart sequential strategy that saves a lot of time. And I won't even ask you, because I think you're going to answer yes, that this is sensible, that if we can reuse our 3 factors that we've already studied, and then just augment it with the additional axial points, which are represented by stars on the outside, we can form this central composite design by building it up from the beginning of the 2-level design and save by only doing these additional 8 runs. So this is a very cool way of doing DOE, and is part of our strategy of experimentation. Very sensible. So here now are the results, and this is the factorial part that we ran, and we saw some promising outcomes here at the center and one of the factorial points. But the trouble was we couldn't fit that center because of only having the 2 levels in the center of everything. So we now augment the design, and we find that with these axial points that are going up above and down below and back and forth, higher and lower, all the way through, plus some additional center points, very promising results that we then can fit, as I'll show you in this design expert demonstration. I'm going to close this out and open up a new design, which is the optimization. And here are the results that I just showed you on the tensile strength, and you see some really good results. I can show the space point type, and we can see what we have here in randomized order. And here we have some center points. Here we have some center points in the original block. And the way this was done was simply by augmenting the design from the original factorial with center points. Let's say we did a 2 to the 4 factorial with center points. Then once you see the curvature is significant, you can go to the augment design and augment it. And the program automatically knows that it should go to a central composite and that this will be an RSM design. And if you go with the defaults, which are presented by George Box, you'd end up with this recipe sheet with the second block containing those axial points. So that's how it's done. It's super easy. using Design Expert. And here are the results that the engineers came up with. And when you fit this to the quadratic, which has got squared terms, and everything's, looking really good from the significance of things, and no abnormalities in the diagnostics, we end up with this super duper 2D graph with color coding, and we can see that there's some really good results over 50,000 in this hotspot. And then using the 3D surface, we can get a really good view of the peak. And we can also slice this current, which is off to the right, back and forth, and we can see kind of where that current needs to be. And finally, we can do a numeric optimization and just simply tell the program to maximize to a stretch target. I'm just going to go for the moon here and say 60,000. No, we're not going to get there. See, we're getting up to 54,000 by getting the current up to near the max, at the max, and then it gives us the exact, angle and substrate thickness. And then we could do one more graph here, which is really showing the desirability of the outcome. And so this is the absolute peak here. Do you like that? Raise your hand if you do. Think of yourself as being a welding engineer and coming up with this result. Isn't it wonderful? Yes. Okay. Thanks, Alan, and all the way down for participating to Zach. E to Z. All right. So, mission is accomplished. Well, is it? I mean, it looks pretty good at this point, right? But we really need to confirm the results. Can't emphasize that enough. Now, one way that this could be done is you could take the numeric optimization, and the program will remember this, and when you go to confirmation, it'll give you the setup that you want. And then you have an option to do a number of confirmations. One wouldn't be sufficient, of course. I'd recommend, probably 6, not 61, but 6. And, hopefully you would get, big numbers, over 50,000 all the way down. If for some reason the weld started coming out unusually low, what will happen is you'll end up with showing up red in this bottom screen. And that means that you've kind of got to go back to the drawing board. Now, why would that happen? Being a chemical engineer, I've worked on process development, R&D, I've gone out of the plant, tried to confirm things, and things don't work as well. Why is that? Who knows? You have to start over, think about, is it different raw materials, different operators? What's the environment down out in the field when you're actually trying to do these welds? A lot of things can happen. So one thing would be a one-up confirmation. I would do that at the R&D center, the pilot plant. And most often when you do that at the R&D and so forth, you will get good results. And in that scenario, of course, we would be getting more like 55,000, in big welds like this, right, on the line. And if that was the case, then of course it would fall within the range and it would be good, but we still aren't really sure it's going to work in the field. But what I like for the final confirmation is actually to do something called a ruggedness test. And this ruggedness test is something that we did when I worked at General Mills Chemical in Henkel of Dusseldorf. We would go out and we would do method developments, and then we would test the methods in the lab QC. And oftentimes we had to do these ruggedness testing because they would recycle reagents. They'd use lower level operators, not PhD analytical chemists and things like that. So I like this ruggedness test for any type of process, whether it be a method or any type of manufacturing. And a good standard for this, if you want to make a note of this, never mind all my other scribblings, but is the ASTM E1169 ruggedness standard. And there's more words to it, but if you look up ASTM E1169, you'll find it. And, I'm a member of the committee that developed this, so I'm biased, but I think it's a very good way to test and do a confirmation. And what we're going to do here is we're going to use a resolution 3 Plackett Burman design, which I mentioned earlier. So it doesn't take a lot of runs, but this way you can test a lot of different factors all at once that might cause your test to fail, your method to fail, your process to fall apart, or whatever it is you're trying to test, the equipment or whatever it might be. All right, well, I guess you didn't have to write that down because it's on slide 21, and you'll be able to pick that up when you pick up the slides off of our site. So there it is there. It's a special application of a statistically designed experiment. It's multi-factor. But what's really good is you can do a large number of possible factors by using this Plackett Burman. Now, by only doing 2 levels, that'll make it easier as well. But here's the Plackett Burman design, or the PB design. And this came in actually before George Box developed RSM, but George Box was working during World War II under the tutelage of his father-in-law, Sir Ronald Fisher, and learning all the tools of DOE. But it was a couple other UK statisticians, Plackett and Burman, that developed these designs, which are unique for being multiples of 4 versus the classical 2-level, or powers of 2. They're 2-level designs, but they're multiples of 4. And that gives us more flexibility. And they're typically done saturated. For example, with 1 less number of factors, like K is equal to 11 and N is equal to 12. That would be a good Plackett Burman design I would recommend. Now, if this test reveals important effects, we can then fold it over. That means a second block with the runs done at levels opposite. And this tool, I'll demonstrate for you, is available in Design Expert. So now to achieve the score, which is the last part, the R, let's see if the welding process stands up to 11 factors of concern, ambient conditions and such, with ranges being set to span the majority, maybe 95% of the normal variation, based on historical records. And it turns out that the 12 runs will provide adequate power, more than 80%, to see the differences that they're interested in seeing. So that's something you have to check. Very important to check the power to make sure that you're not going to overlook something that's really important. Here are the results that we get. Now I'm just going to show the half normal. I will bring up the weld ruggedness just to show the fold over, but it turns out that we can use this half normal plot. And I gave a talk, and I think others from studies have given a talk on how this works. But basically what you're looking at the bottom on this half normal plot is the absolute value of the effects, and the maximum effects that we're seeing on this axis is 217, which is less than what they felt was important. I think earlier I showed somewhere what that was, but it was less than, this is less than what they considered important. And at the beginning, just for perspective, on their first design, they were seeing effects that went all the way to over 2,000. So basically what we have here from this ruggedness test is nothing significant and nothing important, which is the absolute ideal situation for a ruggedness test. So what do you think? Looking at the peak over 50,000 and the fact that when we threw in 11 factors against this process, the biggest effect that comes out is only a couple hundred PSI on tensile strength. Do you think we should celebrate? Yes? Yeah, okay, hands are coming up like crazy all over the place. Well, I mean, naturally, when we provide a demonstration like this of the SCOR, the screening, characterization, optimization, and ruggedness, we want to show something that was successful. But I will say that if for some reason you didn't succeed in seeing factors that get the job done, at least you've done a very thorough, statistically valid test. And even to be able to say that we did this and it didn't work is a huge advantage. Believe me, I've done enough process troubleshooting where people just start doing this and that at random to know that if you do a planned experiment that's multi-factor and you do it in a statistically rigorous way, you're going to come out ahead no matter what. So that's my story, and I'm sticking to it. it's good to know the score. It's good to know about two-level design, multi-factor design, knowing what type of design to pull out in terms of the right resolution, using resolution 4 for screening, the resolution 5 for characterization, using RSM for optimization, but only if you see curvature, and then using one of these Plackett Burman resolution 3 for ruggedness, or a standard red design from the standard design builder, but I definitely recommend the Plackett Burman at the end. And hopefully everything works and we can party on. If it doesn't, you know, we've learned something and we just have to go back and try something else. Remember, we need to have a good invention at the beginning. And if it's not good at the beginning, you're never going to get through to the end. So it may take a little more invention. That concludes my presentation. I do want to suggest that if you want to learn more about these tools that I've used, you might go with this 1-2 punch of DOE Simplified, me being the main author, and Pat being the mastermind on these first two, and then merging in Martin, our PhD statistician, on this next level, which is the mixture design for optimal formulation. And that's kind of a whole nother topic, but there is a strategy of experimentation for this as well. But mainly my focus, as I mentioned at the beginning, is on the process side, which is covered by DOE/RSM Simplified. Now, just a little aside here is kind of a PS, postscript, is Paul Nelson, who is a very sharp statistician with our reseller Prism in UK. He came up with this idea of a range finding ahead of time, which is very important. And I should have really mentioned this on the strategy, because not only is it invention, but before you can really start testing lots of factors, you have to really think about what ranges should we test and are the ranges safe? So one approach to this is just trying different factors one at a time, but a more sophisticated multi-factor approach that doesn't involve too many runs is called a scoping design. And you can see more about this at the Prism site on scoping designs. And there is a way to set this up in Design Expert. It takes a little bit of a workaround, and eventually it's on kind of our bucket list to come up with this as a tool in Design Expert. We have lots of other things that we're still working on in the meantime. Be on the lookout, by the way, for version 13 coming up. This is the keynote address. Well, I would really say more of a kickoff for our online summit. And next is going to be Pat Whitcomb, and he will tell you what we do have coming up in version 13, amongst other things. We won't have the scoping design yet that I'm aware of, but it can be done. But I definitely would recommend you take a look at this website and take a look at the scoping design, because it's a really cool way to do the forcing settings at the all plus level and other settings that are at the all minus level, or whatever you think is going to be troublesome. But then part of this is also to do the current operating conditions as a center point. So to me, it makes a lot of sense. I haven't actually tried it, but I do agree with Doug Montgomery, who is really an expert on DOE, picking up from George Box, Hunter and Hunter, with his book, Montgomery's book, Design and Analysis of Experiments. And Doug says that about 80% of your success in conducting a design experiment really comes from the pre-experimental planning. Good advice. So then to conclude, going back to our SCOR and knowing the SCOR, this provides a tried and true path. As I mentioned, it really can't fail to be productive, whether it meets the objectives or not, provided it's powered up properly. By the process of elimination, you're going to come out ahead. Another thing I like about the SCOR is it's sequential. And that's really good to be adaptable to whatever is going on at any given step. So you break down into small steps, and a general rule is to put no more than 25% into any DOE, any particular experiment. So that leaves you a chance to do, maybe four experiments. which is plenty for the score. Now, in this case, by breaking it into the small steps, if they would have started with all 11 factors and gone straight away into an RSM, that would take 96 runs for a central composite. Even if you go to an optimal design, which is an option in Design Expert, still is a lot of runs. We ended up doing only 50 runs. We had 20 in the screening, which is the MR4 plus 2. We did 22 characterization, which was the full factorial on 4 factors, and then some center points. And then we augmented it using the tools in Design Expert with the star points or the axial points. And so that's only a total of 50 versus 96. It's practically half the number of runs. So it's really a very flexible, efficient, and sensible approach to the score. So this score is a way to go, or something like it. It provides maximum efficiency and effectiveness because of its flexibility for the development, of a process that meets your requirements and that's robust. It's a sure path. So I thought that whether you're new or experienced at doing DOE, this talk would be for you and your organization's bottom line, but you be the judge and tell me by raising your hand if you think this is helpful. Adnan, thank you. Angelica, going down to the bottom. 269, Yu Sin. Wendy, etc. Wayne, thank you. Much appreciated. All right. Now, if you want to learn more, I mentioned the books that you can pick up. Those are also available as ebooks internationally via Amazon. But if you want to move more quickly, consider applying yourself to some of this new distance learning that we've developed as a result of the pandemic. We've shifted over from in-person classes and pivoted to distance learning, or DL. Go to our website and click this Learn DOE link. And then if you like what you see, follow up with an email to workshops@staties.com and get a quote, and be sure to request the DOE Summit discount. We have a modern DOE for process optimization coming up in July, but it is limited to 20. And I expect that's probably going to sell out. We'll have more classes coming up throughout the rest of the year on modern DOE. And some probably will be set up at times that are more convenient internationally for, let's say, the far East Pacific regions, Australia, New Zealand, places like that. We've developed some classes to teach some of the presentations, such as the designed experiments for pharma. We have one of those classes coming in late evening, our end, to accommodate some users in Singapore and elsewhere. So lots of options here. But anyways, you'll see it under the Learn DOE, and you can always follow up with workshops to learn more about it and get a quote. We also have mixture classes, which I highly recommend. I'm really fond of the mixture design for optimal formulation as a chemical engineer. So don't overlook that if you're doing formulations. That concludes my presentation, and it's within the hour that I was hoping for, and probably as much as you can absorb anyways in one sitting. So thank you for attending. Be sure that if you have questions that you email me. I would be very happy to hear from you. So thanks. Much appreciated. I'm going to conclude the presentation. I'll stay on for just a few minutes if there's any questions on the chat, but again, I would prefer that you send by email. Thanks again, and good night, or good morning, or good afternoon. Goodbye.